In this lecture, we're going to titrate a weak acid with a strong base. The example that I would like to do is to titrate 50 milliliters of 0.1 molar benzoic acid. This is a weak acid. We're going to abbreviate it HA, which is just the generic abbreviation for a weak acid. It has a Ka of 6.3 times 10 to the minus 5. We are going to titrate this with 0.1 molar potassium hydroxide. Potassium hydroxide is, of course, a strong base. So in any titration, one of the components must be strong to force the reaction to go to completion during the titration. The strong base would be what's in the burette, and the weak acid in this case would be your analyte. So you would have these 50 milliliters of analyte in an Erlenmeyer flask below your burette through the titration. Now, in a typical titration problem, you're asked to calculate the pH at different points in the titration. And for this particular titration, we want to calculate the pH after different volume additions of the 0.1 molar potassium hydroxide. We're going to calculate it before we add any potassium hydroxide. And then after we've added 10 milliliters, 25 milliliters, 48 milliliters, etc., 50, 51, 60, and 100. When I do the titration of a weak acid or a weak base, these are the things that I like to keep track of in my table. It's a little bit different from how we set up the strong acid, strong base titration. Here, instead of keeping track of the number of moles of protons, I'm keeping track of the number of moles of benzoic acid and the number of moles of its conjugate base, which is benzoate. The pH, of course, is the thing that we want to calculate at these various points in the titration. So I've labeled these various points with letters, and I want to go ahead and carry out the calculation for each of them in turn. Now, before we add any KOH, we are just dealing with a weak acid, 0.1 molar benzoic acid with this Ka. So this is a classic weak acid calculation. You can calculate the pH using the techniques that we learned about in Chapter 13. I will go over that briefly here, but if you want more detail, you should certainly go back to the Chapter 13 for review. So benzoic acid dissociates in an equilibrium to produce its conjugate base, which I'm just calling A minus here, but it's benzoate, and a proton. Now, we could make an ice chart under this and figure out what X is, and X would be equal to the proton concentration, okay? So we can make a shortcut to say that X, or the proton concentration, is approximately equal to the square root of the initial concentration of benzoic acid times the Ka of benzoic acid. And if I really want to make that assumption, I have to check it. So I have to look at 100 times the Ka value. The Ka is 6.3 times 10 to the minus 5. So 100 times Ka is 6.3 times 10 to the minus 3. And this is well below the initial concentration of benzoic acid, which is 0.1 molar. So the assumption is safe, and I can assume that this is going to be approximately equal to the square root of the initial concentration of benzoic acid times the Ka. So my proton concentration is 0.0025, and that is going to be, of course, a molar concentration. I can take the negative log of that to get the pH. So I can put that pH value into my chart here, 2.6. It's an acidic pH, which makes sense because benzoic acid is a weak acid, so I expect an acidic pH. It's not as acidic as it was when we had 0.1 molar hydrochloric acid, as in the strong acid, strong base titration, but it's acidic, which is what we expect for benzoic acid. Now, I also want to figure out how many moles of benzoic acid I have at this point before I add any KOH. And the reason for that is really just because I want to, it's going to be useful later for accounting purposes. So the way that I figure that out is by taking the volume and multiplying it by the concentration of benzoic acid. So 50 milliliters is equivalent to 0.05 liters. I multiply that by the molarity to get 0.005 moles of benzoic acid. That's important because down the line, in the next calculation, you're going to see that that number is important. At the beginning, I don't have any benzoate conjugate base to speak of because dissociation is negligible, so I can just assume that that's 0. All right, now let's do the calculation for the pH after I've added 10 milliliters of KOH. So down here, letter B is adding 10 milliliters of KOH. So 10 milliliters is 0.01 liters. I'm going to multiply that by the molarity of the KOH. It's 0.1 molar. And that tells me that at this point in the titration, I have added 0.001 moles of hydroxide. Think about what that hydroxide does. If I add hydroxide to benzoic acid, the hydroxide is going to accept benzoic acid's proton to make water and benzoate, which is the conjugate base of benzoic acid. This reaction is going to go to completion because hydroxide is a strong base. So because it goes to completion, when I want to figure out what's going on here, I'm going to make an ICF chart, initial change final, instead of an ICE chart. And I'm going to do my accounting. So I know at the beginning I had 0.0050 moles of HA, and I'm adding 0.0010 moles of hydroxide. I'm using the number of moles here rather than the concentrations. You could put the concentrations, but it's just easier to put the number of moles at this point so we can kind of consider the stoichiometry on a mole-to-mole basis. I start out with no benzoate, and I don't really care about water because it's not going to influence the pH. Now, the number of moles of HA is more than large enough to consume all of the hydroxide that I'm adding. And after it does that, I'll be still left with 0.0040 moles of HA. The hydroxide will be all consumed. And on the reverse side of the reaction, I'm going to be creating benzoate, the conjugate base. So I'm going to be creating 0.001 moles of A- or benzoate, the conjugate base. What kind of solution is this now? Remember, this is a weak acid and its conjugate base. I hope that that looks familiar because whenever we have a weak acid and its conjugate base, that is a special type of solution. It's a buffer. And of course, we know how to calculate the pH of a buffer. We need to use the Henderson-Hasselbalch equation, which is pH equals pKa plus the log of the concentration of base over the concentration of acid. So now we can just plug in our values to figure out the pH of this buffer. Negative log of the Ka is 6.3 times 10 to the minus 5. And here, because this is a ratio, the total volume is going to be the same in the denominators of both the concentration of weak base and the concentration of weak acid. So those total volumes would cancel. So I can actually just plug in the number of moles of each, ignoring the total volumes. And again, I can only do that because this is a ratio and those total volumes would cancel anyway. So the pKa is 4.2. This term comes out to negative 0.6. So after you do this calculation, you should get a pH of 3.6. So we can put that into our chart. Okay, so we have a pH of 3.6. Now I have 0.004 moles of benzoic acid, and I have created 0.001 moles of benzoate. Let's look now at what happens when I've added 25 milliliters of KOH. But I will save that for the next video.